Okay, this lecture has to do with mixing chambers and heat exchangers. And both of these are thermodynamic systems that are used frequently. A heat exchanger is set up to transfer heat between two fluids without mixing them together. Okay, one of the most obvious examples is your car's cooling system. Okay, your car has cooling fluid, goes through the radiator, goes around the engine to try to cool it, and it does not mix. That cooling fluid does not mix with the rest of the components inside your car. At least it shouldn't, right? It goes through the radiator, cools off using the natural convection of the airflow, and then it goes back through to the motor to try to cool it off again. And so think of, when you think of heat exchanger, think of your car and its cooling system, radiator, but basically remember that they do not mix. Okay, so there's no mixing with the heat exchanger. But then we have a mixing chamber, and that involves obviously the direct contact between the fluid streams. Okay, that's where they do mix. And so the real difference here between the mixing and non-mixing problems is that with the mixing, the mass flow rates in combine to get one mass flow rate out, typically. I guess it doesn't have to, but a lot of times what you'll have in a mixing type situation is you might have m.1, m.2 coming in, and they mix, and then coming out is m.3, and we have the relationship that m.3 is equal to m.1 plus m.2. So that's pretty obvious. Whereas if you have a heat exchanger, the two streams have their own constant mass flow rates, and they don't interact from a mass perspective. They only interact from a heat perspective. They may exchange heat. And so I have a couple examples here that we'll do involving heat exchangers and mixing chambers. And both of them, I think you'll find, are pretty simple. There's not too much to them. Okay. Let's first talk about some typical assumptions with heat exchangers and mixing chambers. First, they don't do any work. Okay. And the second thing is that when you consider it as a system, there is no heat transfer, and it's important that you understand that as we're talking about that as a system. Obviously, they will transfer heat between themselves, but if you look at the entire system, there is no heat transfer in and out, okay? And so there's heat transfer internally between the two flows, but not outside, okay? And so typically when we draw a boundary around the whole system, we'll say there's no heat transfer in and out of the boundary, only heat transfer inside between the two flows. So no work, no heat transfer, and of course, you know, no kinetic potential energy changes are typical with mixing chambers and heat exchangers, okay? And so the fundamentals really break down. They become very simple here. Fundamental equation, and I probably should have put a dot on these, is that the energy in, the energy flow in is equal to the energy out. That's pretty much it. And so that's the fundamental difference between the two things. So that's the difference between them is energy in is equal to energy out as a flow, and you've got the m dot h in, the sum of all the m dot h's in is equal to the sum of all the m dot h's out. Okay, so it breaks down to a pretty simple equation, and that's really all there is to it. Okay, so let's take a look at a couple of examples here, and I think that will help us to understand what's going on here. First is we have steam condensed on the shell side of a heat exchanger at 85 degrees Fahrenheit. The cooling water enters the tubes at 60 degrees Fahrenheit at a rate of 138 pounds per second and leaves at 73 degrees Fahrenheit. Assuming the heat exchanger to be well insulated, that means overall Q equals 0, right? Overall, no heat transfer. Determine the rate of heat transfer in the heat exchanger inside, okay? So it looks like it's a little bit strange to say Q equals 0 and then you're trying to determine the heat transfer, rate of heat transfer inside, okay, and the rate of condensation of the steam. Okay, so that's both of them that we'll need to get. Okay, so let me draw a picture here because I think that'll help us understand what we're doing here. Let's try to draw this. Okay, I'm going to draw this here. This. Okay, let's draw the cooling water flow kind of like this. You get the idea, something like that. Okay, so you've got cooling water coming into the system at 60 degrees Fahrenheit. It leaves at 73 degrees Fahrenheit. And then what you've got coming in here on the other side, this is going to be steam at 85 degrees Fahrenheit. And this is going to be this is going to be saturated liquid at 85 degrees Fahrenheit. And I chose this because this is kind of some typical language that I thought might be confusing for students. When they say steam is condensed, what they're really saying is that you've got saturated vapor, steam, and you're turning it into saturated liquid, because that's really what condensation is all about. You're taking the vapor and turning it into the liquid. And so you'll notice that the steam temperature does not really change during the process. Therefore, don't use specific heats for steam, because that's not going to help you because the temperature doesn't change. Okay, so specific heats are not a good way to do it. You have to try to look at the basically what they call the latent heat of vaporization, or the evap term that we'll have in our text in the tables. Okay. So this is water here, this liquid water, just standard stuff. And this, by the way, you might say, well, what is this thing? But this is probably like a power plant. A power plant is going to condense its steam once it's done and turn it back into liquid. And it's going to use some external water. This is why a lot of power plants are near rivers or lakes and things like that, because the lake could be used as part of the power plant for cooling effects. Okay, and so we've got both of those going on there. So let's write out some equations here and see what we can do here. So we write energy in equals energy out. And then we can also express this, of course, as energy in minus energy out equals 0. And then what we can do is we can write that also for each stream. So we can say the energy in minus the energy out for the liquid water plus the energy in minus the energy out for the steam, we'll just call it steam, is equal to 0. And then what we can do is for the liquid water, we can definitely apply specific heats. Okay? And so what we have here is you have the mass flow rate of the water times the specific heat of water, this is liquid water, okay, times the temperature difference in minus out, that would be 60 minus 73, okay. Well, let me just write this as right now we'll just write this as variables. T in minus T out plus energy in minus energy out of the steam. Well, that's really going to just be the mass flow rate of the steam times the evap, H evap of the steam. And so what we've got there is you've got both those, and so you've got to put those together like that. Okay, so now let's fill in some numbers here. You've got the mass flow rate of the water is given as 138 pound mass per second. The specific heat of water pretty much is going to be 1 BTU per pound mass Fahrenheit. And then this is, of course, going to be 60 minus 73 Fahrenheit, plus the mass flow rate of the steam, which we don't know, times the HEVAP for steam, which turns out to be 1045.2. You look this up in the tables, BTU per pound mass. You look that up for tables, that's going to be, the HEVAP is going to be at 85 degrees Fahrenheit for steam. So look that up in your tables. You should be able to find that as being 1045.2 BTU per pound mass. Okay? So if you set this all equal to 0, you can then solve for the mass flow rate of the steam, and you get 1.72 pound mass per second. Okay? So we've got that part. So I've got, basically that was just the first law, energy in minus energy out, and I did energy in minus energy out for each stream. Okay? So I did energy in minus energy out for the liquid water, and then I did energy in minus energy out for the steam. And of course, the difference in the steam is simply going to be the evap term times its mass flow rate, because that's the only thing different between those two. By the way, you could have also, instead of using HEVAP, you could have looked up the H's on both of them. Okay? You could have looked up the H. You could have had an H1 minus an H2, and you could have looked up H1 for steam and H2 for the saturated liquid. That would be, H1 would be saturated vapor at 85 degrees Fahrenheit, and H2 would be saturated liquid at 85 degrees Fahrenheit. But obviously the difference between H1 minus H2 would be the HEVAP term. Okay, so it's the same thing. Okay, it really is the same thing. But so there's the mass flow rate of the steam, and it says also determine the rate of heat transfer in the heat exchanger. Okay, well for that, that's going to be in BTUs per second, and so that's not going to be the mass flow rate. It can be a little bit confusing because I thought you said, you might have thought I said Q equals 0, but really Q equals 0 around the whole boundary. Okay. If I draw this boundary here, we say Q equals 0. But inside, there's clearly heat transfer going between the two substances. Okay, and the easiest way to look at the rate of heat transfer is simply to look at one of the two substances. So, for instance, let's take a look at the water. Okay, the change in energy of the water. Okay, that's simply going to be, just as I've written before, the mass flow rate of the water times the C for water times T in minus T out. Okay, and so what you've got there, it's already given up there. So all you have to do is really just multiply that piece. You got 138 pound mass per second times 1 BTU per pound mass degrees Fahrenheit times 60 minus 73, and of course it'll be negative. It'll be minus 1794, and if you work out the units, you'll get BTUs per second. Okay, now that's negative because the heat is going into the water. It's not leaving the water. Okay, that's why it's negative. Obviously, it would be positive if I looked on the steam side. Okay, so that's what's going on with that problem. So, okay, the next one here is a mixing problem, okay? And so the thermostatic mixing valve is designed to mix very hot water at 140 degrees Fahrenheit with cold water at 60 degrees Fahrenheit to ensure that the water is at a uniform temperature. In most households, your actual hot water heaters run hotter than 120 because it's good to, it helps keep some of the germs and some of the bad stuff in the water from happening if you can heat your hot water heater to 140. But the problem with that is that you don't want hot water coming out of your faucets at 140 Fahrenheit. That's a bit too much for hands and things like that, and you can kind of burn your hands. And so a lot of homes, they regulate it down to 120. And so they use this thermostatic mixing valve basically to mix some of the cold with some of the hot so that you get the desired temperature, okay? And from a thermodynamics perspective, this is a pretty simple problem, but I think it's an interesting problem, and at least it does involve taking a look at mixing. And so let's think of this as, okay, here is your hot water heater, okay? Water. And so we're thinking that it's probably going to have it at 104 degrees Fahrenheit. And then you're going to take some of that hot water and you're going to bring it in and you're going to combine it, this is our mixing chamber or whatever, and you're going to combine it with your city water, okay, which is going to come in at a relatively cool 60 degrees Fahrenheit. And this mixing valve will then combine the two flows to give you what you want, which is 120 degrees Fahrenheit water. And let's say, for example, that you want to make sure that at the most you can get 5 gallons per minute of hot water. That doesn't seem too unreasonable, okay? And so if you want your system here to provide up to 5 gallons per minute of hot water at 120 degrees Fahrenheit, determine the volume flow rate of the hot water and the ratio of hot to cold water, okay? The only reason I express this as a volume flow rate is because most of the time we think of water in terms of volume, and certainly in this case we have 5 gallons per minute at 120, so we're thinking of this as volume. But the real analysis, you do have to put this in terms of mass flow rate, okay? So let's think about some numbers here. We've got 5 gallons per minute, okay? All right. That's really, if you consider a gallon of water, roughly a gallon of water is 8.34 pound mass. Therefore, 5 gallons per minute is going to give you about 41.7 pound mass per minute, and that's going to be equal to about 0.695 pound mass per second, okay? That's what we want. We're going to call that m dot out, okay? That's right here. That's the mass flow rate of what I want out, okay? I want 0.695 pound mass per second out, okay? And so let's now go ahead and put our analysis in here. We've got that the energy flowing into this mixing valve is equal to the energy rate flowing out of it, okay? And so what do we got flowing in? We got two streams flowing in. You've got an m dot hot, okay, I'm going to call that H, put that right here, okay, and it's going to have its own enthalpy. We'll call it H hot, okay, plus it'll have an m dot cold plus m dot cold times its own enthalpy, H cold, and that combines to get you a total mass flow rate of m dot out times what we'll call the H coming out is H out, okay? So the HH is the enthalpy of the hot side, HC is the enthalpy of the cold side, and H out is the enthalpy of what's coming out of your faucets when you want hot water, okay? And so, and then those are your mass flow rates, and obviously, we know that the mass flow rate of the hot plus the mass flow rate of the cold gives you your mass flow rate out, okay? So we can exploit that, because what I can say here is that my mass flow rate hot is really equal to the mass flow rate out minus the mass flow rate of the cold, right? And so I can substitute that into my relationship here, and I can say m dot out minus m dot cold, okay, times H hot plus m dot cold plus H cold equals m dot out H out. Okay, this is some simple algebra there, just a substitution, right? And then what I can do is I can write this out a little bit. I'm going to multiply this out. So I'm going to have m dot out times HH minus m dot C times HH plus m dot C HC equals m dot out H out. Okay, so that's just multiplying the HH into the parentheses. And then what I can do now is simplify this. I can write m dot C is equal to HC minus HH equals m dot out times H out minus HH, like that. Okay, so that's just simply grouping the two terms together, the m dot C terms and the m dot out terms, okay? And then what I can do is I can solve for the m dot on the cold side. It's going to be equal to the m dot of the total out minus H out minus HH divided by HC minus HH. Okay, these are all in enthalpies. Now, I don't have enthalpy data. What I have is temperatures. So remember, though, that if I have, this is m dot out, what I can do is the difference between H out and H8, right? Remember, H out is 120 degrees Fahrenheit. That's the stuff that comes out of our faucets at 120 degrees Fahrenheit, and HH comes out of our hot water heater at 140. So the difference between those two enthalpies can be expressed very simply as equal to the specific heat C times T out minus TH. And of course the bottom part there, HC minus HH, can be equal to the specific heat of water times TC minus TH. Okay? Now those the specific heats basically will cancel, okay? Because really the specific heat of water does not vary much with temperature in this range, okay? They're all pretty much around 1 BTU per pound mass Fahrenheit. So pretty much you can cancel C. And what you can do here is then you can express this as your mass flow rate out, which is 0.695 BTU per pound, pound mass per second, of course, times what you have on the top minus the bottom here. The top is going to be 120 minus 140, and the bottom is going to be 60 minus 140. So if you work that out, your m dot C is equal to, if you, basically this part inside the parentheses, this is going to be minus 20 divided by minus 80. And so that's basically 1/4. So MC is going to be equal to the cold side, is going to be 0.695 pound mass per second times 1/4. Okay? And so what you have there is it's basically just 1/4 of the required flow comes from the cold side. So if you work that out, okay, what you get here is 0.25 times 0.695. In terms of pound mass per second, you get 0.174 how mass per second. But the question said give it to me in a volume flow rate. So really in a volume flow rate, it's going to be 1/4 of the total output. So if you want the total output to be 5 gallons, okay, 0.25 times 5, you're going to be drawing in 1.25 gallons from your cold side. And then on the hot side, you're going to be drawing in 3.75 gallons. That's basically what that's saying, okay? And they're going to combine to give you the 5 gallons that you want at 120 degrees Fahrenheit. And again, that's just a very simple application of the first law of thermodynamics. All you have to do is make your substitutions and solve them. By the way, it also asks for the flow rate of the hot water. The hot water is going to be so this answer here is 3.75 gallons per minute. And the ratio of the hot to cold, well, that's just going to be 3.75 GPM divided by 1.25 GPM, right? The hot divided by the cold, and that's just going to be 3, okay? So basically what the thermostatic mixing valve that you might have in your home is just going to ensure that you have 3 times more hot water coming from your hot water heater to the cold water coming from the city, and when they mix together, they will give you that temperature that you desire when you really want hot water at your faucet. So basically just a couple of very simple examples. There's mixing, and another example using a heat exchanger. So hopefully this helps you as you try to work with these two types of problems, but I think you'll find that the homeworks are pretty easy with that.